An adiabatic process is one that occurs without transfer of heat or matter between a thermodynamic system and its surroundings. In an adiabatic process, energy is transferred only as work. The adiabatic process provides a rigorous conceptual basis from the theory used to expound the first law of thermodynamics, and as such it is a key concept in thermodynamics. Some chemical and physical processes occur so rapidly that they may be conveniently described by the adiabatic approximation, meaning that there is not enough time for the transfer of energy as heat to take place to or from the system. By way of example, the adiabatic flame temperature is an idealization that uses the adiabatic approximation so as to provide an upper limit calculation of temperatures produced by combustion of a fuel. The adiabatic flame temperature is the temperature that would be achieved by a flame if the process of combustion took place in the absence of heat lost to the surroundings. Description: a process that does not involve the transfer of heat or matter into or out of a system, so that Q equals 0, is called an adiabatic process, and such a system is said to be adiabatically isolated. The assumption that a process is adiabatic is a frequently made simplifying assumption. For example, the compression of a gas within a cylinder of an engine is assumed to occur so rapidly that on the time scale of the compression process, little of the system's energy can be transferred out as heat. Even though the cylinders are not insulated and are quite conductive, that process is idealized to be adiabatic. The same can be said to be true for the expansion process of such a system. The assumption of adiabatic isolation of a system is a useful one, and is often combined with others so as to make the calculation of the system's behavior possible. Such assumptions are idealizations. The behavior of actual machines deviates from these idealizations, but the assumption of such perfect behavior provides a useful first approximation of how the real world works. According to Laplace, when sound travels in a gas, there is no loss of heat in the medium and the propagation of sound is adiabatic. For this adiabatic process, the modulus of elasticity equals gamma p, where gamma is the ratio of specific heats at constant pressure and at constant volume, and p is the pressure of the gas. Various applications of the adiabatic assumption for a closed system. One may write the first law of thermodynamics thus: delta U equals Q plus W, where delta U denotes the change of the system's internal energy, Q the quantity of energy added to it as heat, and W the work done on it by its surroundings. If the system has rigid walls such that work cannot be transferred in or out, and the walls of the system are not adiabatic and energy is added in the form of heat, and there is no phase change, the temperature of the system will rise. If the system has rigid walls such that pressure volume work cannot be done, and the system walls are adiabatic, but energy is added as isochoric work in the form of friction of the stirring of a viscous fluid within the system, and there is no phase change, the temperature of the system will rise. If the system walls are adiabatic but not rigid, and in a fictive idealized process, energy is added to the system in the form of frictionless, non-viscous pressure volume work, and there is no phase change, the temperature of the system will rise. Such a process is called an isentropic process and is said to be reversible. Fictively, if the process is reversed, the energy added as work can be recovered entirely as work done by the system. If the system contains a compressible gas and is reduced in volume, the uncertainty of the position of the gas is reduced, and seemingly would reduce the entropy of the system, but the temperature of the system will rise as the process is isentropic. Should the work be added in such such a way that friction or viscous forces are operating within the system, then the process is not isentropic, and if there is no phase change, then the temperature of the system will rise. The process is said to be irreversible, and the work added to the system is not entirely recoverable in the form of work. If the walls of a system are not adiabatic, and energy is transferred in as heat, entropy is transferred into the system with the heat. Such a process is neither adiabatic nor isentropic, having Q and GT 0 and delta S and GT 0 according to the second law of thermodynamics. Naturally occurring adiabatic processes are irreversible. The transfer of energy as work into an adiabatically isolated system can be imagined as being of two idealized extreme kinds. In one such kind, there is no entropy produced within the system, and the work is only pressure-volume work. In nature, this ideal kind occurs only approximately, because it demands an infinitely slow process and no sources of dissipation. The other extreme kind of work is isochoric work, for which energy is added as work solely through friction or viscous dissipation within the system. A stirrer that transfers energy to a viscous fluid of an adiabatically isolated system with rigid walls, without phase change, will cause a rise in temperature of the fluid, but that work is not recoverable. Isochoric work is irreversible. The second law of thermodynamics observes that a natural process of transfer of energy as work always consists at least of isochoric work and often both of these extreme kinds of work. Every natural process, adiabatic or not, is irreversible, with delta S and GT 0, as friction or viscosity are always present to some extent. Adiabatic heating and cooling. The adiabatic compression of a gas causes a rise in temperature of the gas. Adiabatic expansion against pressure, or a spring, causes a drop in temperature. In contrast, free expansion is an isothermal process for an ideal gas. Adiabatic heating occurs when the pressure of a gas is increased from work done on it by its surroundings, e.g., a piston compressing a gas contained within an adiabatic cylinder. This finds practical application in diesel engines which rely on the lack of quick heat dissipation during the compression stroke to elevate the fuel vapor temperature sufficiently to ignite it. Adiabatic heating occurs in the Earth's atmosphere when an air mass descends, for example, in a katabatic wind, foehn wind, or Chinook wind flowing downhill over a mountain range. When a parcel of air descends, the pressure on the parcel increases. Due to this increase in pressure, the parcel's volume decreases and its temperature increases as work is done on the parcel of air, thus increasing its internal energy, which manifests itself by a rise in the temperature of that mass of air. The parcel of air can only slowly dissipate the energy by conduction or radiation, and to a first approximation it can be considered adiabatically isolated and the process an adiabatic process. Adiabatic cooling occurs when the pressure on an adiabatically isolated system is decreased, allowing it to expand, thus causing it to do work on its surroundings. When the pressure applied on a parcel of air is reduced, the air in the parcel is allowed to expand. As the volume increases, the temperature falls as its internal energy decreases. Adiabatic cooling occurs in the Earth's atmosphere with orographic lifting and lee waves, and this can form bilious or lenticular clouds. Adiabatic cooling does not have to involve a fluid. One technique used to reach very low temperatures is via adiabatic demagnetization, where the change in magnetic field on a magnetic material is used to provide adiabatic cooling. Also, the contents of an expanding universe can be described as an adiabatically cooling fluid. Rising magma also undergoes adiabatic cooling before eruption, particularly significant in the case of magmas that rise quickly from from great depths such as kimberlites. Such temperature changes can be quantified using the ideal gas law, or the hydrostatic equation for atmospheric processes. In practice, no process is truly adiabatic. Many processes rely on a large difference in timescales of the process of interest and the rate of heat dissipation across a system boundary, and thus are approximated by using an adiabatic assumption. There is always some heat loss, as no perfect insulators exist. Graphing adiabats. An adiabat is a curve of constant entropy on the PV diagram. Some properties of adiabats on a PV diagram are indicated. These properties may be read from the classical behavior of ideal gases, except in the region where PV becomes small, where quantum effects become important. Every adiabat asymptotically approaches both of the axis and the p-axis. Each adiabat intersects each isotherm exactly once. An adiabat looks similar to an isotherm, except that during an expansion, an adiabat loses more pressure than an isotherm, so it has a steeper inclination. If isotherms are concave towards the northeast direction, then adiabats are concave towards the east-northeast. If adiabats and isotherms are graphed at regular intervals of entropy and temperature, respectively, then as the eye moves towards the axis, it sees the density of isotherms stay constant, but it sees the density of adiabats grow. The exception is very near absolute zero, where the density of adiabats drops sharply and they become rare. The following diagram is a PV diagram with a superposition of adiabats and isotherms. The isotherms of the red curves and the adiabats of the black curves. The adiabats are isentropic. Volume is the horizontal axis and pressure is the vertical axis. Etymology. The term adiabatic, Ediabatic, literally means not to be passed through. It is formed from the ancient Greek privative plus delta iota alpha beta alpha tau omicron sigma, able to be passed through, in turn deriving from delta iota and beta alpha nu epsilon iota nu. Thus delta iota alpha beta alpha tau omicron sigma. According to Maxwell and to Partington, the term was introduced by Rankine. The etymological origin corresponds here to an impossibility of transfer of energy as heat and of transfer of matter across the wall. Conceptual significance in thermodynamic theory. The adiabatic process has been important for thermodynamics since its early days. It was important in the work of Joule, because it provided a way of nearly directly relating quantities of heat and work. For a thermodynamic system that is enclosed by walls that do not pass matter, energy can pass in and out only as heat or work. Thus a quantity of work can be related almost directly to an equivalent quantity of heat in a cycle of two limbs. The first is an isochoric adiabatic work process that adds to the system's internal energy. Then an isochoric and workless heat transfer returns the system to its original state. The first limb adds a definite amount of energy and the second removes it. Accordingly, Rankine measured quantity of heat in units of work, rather than as a calorimetric quantity. In 1854, Rankine used a quantity that he called the thermodynamic function, that later was called entropy, and at that time he wrote also of the curve of no transmission of heat, which he later called an adiabatic curve. Besides its two isothermal limbs, Carnot's cycle has two adiabatic limbs. For the Foundations of Thermodynamics, the conceptual importance of this was emphasized by Bryan, by Carathéodory, and by Born. The reason is that calorimetry presupposes temperature as already defined before the statement of the first law of thermodynamics. But it is better not to make such a presupposition. Rather, the definition of absolute thermodynamic temperature is best left till the second law is available as a conceptual basis. In the 18th century, the law of conservation of energy was yet to be fully formulated or established, and the nature of heat was debated. One approach to these problems was to regard heat, measured by calorimetry, as a primary substance that is conserved in quantity. By the middle of the 19th century, it was recognized as a form of energy, and the law of conservation of energy was thereby also recognized. The view that eventually established itself, and is currently regarded as right, is that the law of conservation of energy is a primary axiom, and that heat is to be analyzed as consequential. In this light, heat cannot be a component of the total energy of a single body because it is not a state variable, but, rather, is a variable that describes a process of transfer between two bodies. The adiabatic process is important because it is a logical ingredient of this current view.